We're going. All right. I don't know if this is going to improve the resolution or not, but I have this more blown up on my screen, and I can certainly see it better, but I don't know if you'll be able to or not. Something that's addressed in one of the sections in chapter 18 is the idea of molecular kinetic energy. And there's a branch of physics called statistical mechanics, and it's a way of approaching most especially thermodynamics and developing things from a particle point of view. And you look at individual particles and consider their energies and then move on from there. But when you do that, a lot of what happens in a typical thermodynamics section ends up making a whole lot more sense. But we won't have time to do that. Actually, it's like a 2 semester course at some universities, maybe 1 semester, I'm not sure. But anyway, something they find out from that is that I better write this larger. Uh, Molecular kinetic energy so we'll go with that, is 1/2. And a lowercase m here means the mass of the molecule. And so we'll have that. And it's the average value. And they just use an AV for average. I tend to use an AVG, but don't worry about that too much. But this would be the average kinetic energy of a molecule or an atom of mass m. And it's equal to 3/2 K T, and that's the Boltzmann's constant that I was using yesterday. And I tend to put a subscript of a B on it because we were just using K for thermal conductivity, and you might get confused, but it's a Boltzmann's constant, and it's one that I used the other day. Now, there's another way of writing this V squared average, and if you think about the order that you do things in, you'd first take the square of V and then calculate the average of it. And if you just wanted the speed itself and not the squared, then you'd take a square root. So you'd start by doing squaring the V, then you take the average, and then you take the square root of it. And sometimes this process is just abbreviated. In fact, often it's just abbreviated as RMS. And the RMS stands for the root of the mean, which is a term for average, the root of the mean of the square. And so we'll just write it that. And with that notation, we'll write this as 1/2 mVRMS squared. And so it's like an average velocity. It actually, squaring it has some advantages. So that's the reason that that shows up. Now, this stuff is developed using that ideal gas law that had PV equals capital N times K sub B, Boltzmann's constant, times T. Again, that's different from the chemistry version, which has lowercase n and a capital R times T, which we are going to be using some today. So either one of those things works in this case, but capital N is the actual number of particles, lowercase n is the number of moles. So I know some of you may not have ever had a chemistry class, but 1 mole is equal to 6.02, and then there's a whole bunch of numbers after that, times 10 to the 23rd molecules or atoms or whatever it is that you want to be talking about. So I read not too long ago, but one of Albert Einstein's contributions to science was figuring out a better way to determine the number of atoms in a mole. And that was one of his very earliest contributions, actually. So he was lots of different interests. Anyway, that's another way that this thing could be written. In fact, by the way, this number is called Avogadro's number, and it's written as a capital N with a lowercase a. If we took this equation here, or maybe the 1/2 mvrms squared equaling 3/2, and I'm leaving spaces in here because I'm going to do something to both sides. Multiply both sides by Avogadro's number. And if you multiply the mass per particle times Avogadro's number, you get the molar mass, which is often written with a capital M. So 1/2 capital M VRMS squared. And if you multiply Boltzmann's constant by N sub A, Avogadro's number, you get the ideal gas constant. So this would become 3/2 capital R times T. But just looking at this thing, well, either version of it, I kind of like this one, but and you could just use a KT. In this unit, we're only going to be using lowercase k to stand for Boltzmann's constant. So, oh wait, we just had part of our thermodynamics unit where it was the thermal conductivity. So maybe we better be a little careful. But this tells us these are just proportionality constants, but they tell us that temperature is just a measure of average particle kinetic energy. That's what temperature is, at least for a gas. And if you always wonder just what does it mean to have a higher temperature, well, what it means is the particles have higher speeds, they have higher kinetic energies, and the kinetic energy is proportional to the temperature. So you double the temperature, you're doubling the average particle kinetic energy. So that's pretty neat. And you can solve for VRMS in terms of this other stuff, and it ends up equaling, this is just a little bit of math here, 3K sub B T or over M, or you could also write it as the square root of 3 capital R times T divided by the molar mass. So either way, but you can calculate particle speeds. For instance, let's go ahead and calculate what is VRMS for O2 molecules at room temperature. Whoops, ran out of paper on that one. Anyway, at room temperature. Well, what's room temperature? If we just figure roughly 20 degrees Celsius, add that to 273 degrees Celsius, which is the amount we're above absolute zero, and you get a temperature of about 293 Kelvin. Okay, well, I'll show you how I like to figure stuff like this out. We're going to have just our VRMS is going to equal the square root of 3K sub B times T divided by M. And now we do need to know the value of Boltzmann's constant, which I don't know why it's never stuck in my head, but it's 1.381 times 10 to the minus 23rd. and it's got units of joules per Kelvin. Is what that happens to be. So now the thing we need to know is the mass of an oxygen molecule. Well, um, here's how I do it. An oxygen atom, the most common isotope of oxygen, has 8 protons and 8 neutrons, but we've got 2 of them in a molecule. It's an O2 molecule, and almost the entire mass of the atom is due to the number of protons and neutrons. And so I would just do this. Let's see, we've got a combined 8 protons, 8 neutrons. They have nearly the same mass. In fact, the 3 significant figures they do. But in 2 atoms worth, you'll have 16 protons and 16 neutrons contributing to the mass. So you'll have 32 nucleons. And the average mass of a proton and neutron is about 1.67 times 10 to the minus 27th kilograms. And so the mass of an O2 molecule is going to be whatever you get when you multiply that out. Okay, so about 5.3 times 10 to the minus 26. And maybe we could keep 3 sig figs, so it could be 5.34 times 10 to the minus 26 kilograms. And yep, that's right. Okay, so now we can do this problem. VRMS for an O2 molecule is going to be the square root of 3 times Boltzmann's constant, 1.381 times 10 to the minus 23rd joules per Kelvin, times the temperature, which is 293 Kelvin. So Kelvin will divide out. I'll have joules divided by the mass of this thing, 5.34 times 10 to the minus 26 kilograms. Now, a joule is a kilogram meter squared per second squared. If I divide by kilograms, I'm left with meters squared per second squared, but I take the square root and get meters per second. So unit-wise, I'm in good shape. Okay, so and I get about 477 meters per second. So that's a pretty good clip. That's, oh, let's see, 400 meters per second, it'd be about, uh, no, I don't know how many that is. Oh, 40 meters per second is 90 miles an hour. So this is about 12 times 90 miles an hour, which is around 1,080 miles per hour. So pretty fast anyway. But they're just zipping around in completely random directions. You've got every direction in the air in a room that you could possibly think of and just all that stuff. But that's a way that you can calculate the speed of an oxygen molecule at room temperature. So it jumps out of there pretty nice. Okay, we're soon going to be we're only going to spend about 1 day on it, on the first law of thermodynamics. But the first law of thermodynamics has to do with energy. It's actually a statement of conservation of energy is what it happens to be. And we'll be considering that, but we want to be thinking quite a bit about these energies and things like that. And we're going to be interested in the heat capacities of gases. And the heat capacity that we dealt with earlier, we actually dealt with specific heats where we had things like the amount of heat needed to raise the temperature of something was proportional to its mass, and then times a specific heat, and then times the change in temperature. Well, how do you equate that to gases? Um, it depends on the process. It turns out it depends on, there'll be one type of specific heat where the volume is kept constant. And it turns out that if the volume is kept constant, any heat that you put into there just goes into raising its temperature. But if the volume is not kept constant, then there's a different specific heat that shows up, because at the same time you're adding heat to it, some of that energy is going to go to letting the gas do work on its surroundings. And that's an idea that we're going to address quickly here. But we'll look at the specific heat of a gas, or the heat capacities of gases, first at constant volumes. And it turns out for a monatomic gas, it's one value, and its C sub V is equal to 3/2 R. Now, because we've got that constant here, this will be the molar heat capacity. And when we're talking about dumping energy into a gas, we'll be more interested in counting the number of moles. And so we'll have a different heat capacity there. In fact, in this case, the Q would equal capital M times C sub V times delta T. But that's what it is for a monatomic gas. And for a diatomic gas, it looks a little different. It happens to be, it's 5/2 R. And this is kind of a weird thing. Why should it make a difference? Well, it turns out for a monatomic gas, we say that it has just 3 degrees of freedom. Any heat that you add to that monatomic gas, a monatomic gas would be something like helium, or noble gases, actually. Helium or argon are both monatomic gases. And when you add the heat to there, it goes to increase their kinetic energy. But for kinetic energy, you can go up or down, you can go sideways, or you can go, I don't know, left, right, up, down, and stuff like that. You can only go in 3 different dimensions: the X direction, the Y direction, and the Z direction. But for a diatomic gas, those are things that look like little dumbbells for a diatomic gas. And so you've got 2 molecules that are like that. They can also have rotational degrees of freedom. So the diatomic molecule can either rotate about this axis, or you could draw another axis here and it could rotate about this axis. The third axis, where you'd be looking down the axis of the molecule itself, isn't considered a degree of freedom, because there's not going to be much energy in that rotation around that axis, for one thing, and it's not easy to get it moving very well in that direction as well. So for a diatomic gas, in addition to going in the X, Y, and Z direction, it can also rotate around a couple of axes, and that's why you get a number in this numerator that's 2 more than that number there. So that's kind of a weird thing that can happen. Now, this all sounds kind of theoretical, but I want to show you a table that's actually got more information in it than we want, but a table of molar heat capacities. And it's got different gases listed here. And then there are theoretical values, but for monatomic gases, it just has helium and argon listed. And these are experimentally determined things. And the only one we've talked about so far is C sub V, the heat capacity at constant volume. So you can ignore all the other columns except this one, but you can see the theoretical value, which would be 3/2 R, is 12.47, and both helium and argon agree with that to 4 significant figures. For diatomic gases, it's got a few of them listed here. The theoretical value is 20.78. That's what 5/2 R would be. And they're not bad. Hydrogen seems to be about the farthest off from it, 20.42. Nitrogen is 20.76. That's a little low, but not too bad. It's only 2 parts in 2078. Hydrogen's a little higher, but it's only 7 parts in 2078 parts. So that's not too bad. That's pretty good agreement. Carbon monoxide is about the same as oxygen. So pretty good agreement between theory um, and experimental results in that case. And so they work. Anyway, we can use those things. And as long as we're not worried about getting 4 significant figures, we'll be pretty good most of the time. We'll have a little uncertainty, maybe in our 3rd digit, but not a huge amount. So that's something that shows up there. And let's go back to our other screen here, which I usually forget to do. Okay, we'll be back to that. Okay, now something that's going to help us a bit in some of the problems that we're going to do here today is thinking about the work that can be done in thermodynamic processes. And for starters, I'm going to introduce the idea of a PV diagram. And the P stands for pressure and V stands for volume. And in these diagrams, we always put the pressure on the vertical axis and the volume on the horizontal axis. And the origin is down here. We don't have to worry about negative values because you can't make the volume any smaller than 0, and you can't make the pressure any smaller than 0 either. So we'll be interested in processes like that in these PV diagrams, and a point on here would represent some specific value of the pressure and some specific value of the volume. And in the ideal gas equation we've got, I'll go ahead and use the molar value, where we've got nRT looking like that. If you fix the pressure and the volume and you don't change the number of particles, then you've determined the temperature as well. In fact, if the pressure and the volume are constant on here, you could imagine the pressure times the volume happen to be constant. You'd have a constant temperature then for a particular sample of gas. And what does that look like? If you've got the P on the vertical axis and the V on the horizontal axis, you get hyperbolas. That's like XY is a constant, and it's something that is a curve that looks about like that. And so a curve like this, where PV is constant, is actually, we call it an isotherm. And iso means same, and therm has to do with the temperature. So an isotherm is a curve that looks like that on a PV diagram. But for now, let's think about how a gas could do work. Okay. The only thing it can do is either expand against its environment That means it's going to do work on it. Now, here's where that could happen. Let's suppose you have a cylinder here, and you've got a piston that doesn't let anything leak out of here. And so if this gas that's in here expands, it can push that piston upward and do some work on it. That's a way that a gas could do work. And you can have all sorts of different kinds of work on a PV diagram. You could imagine a situation where the gas goes from here to here. Okay. Well, let's see. Earlier, we learned that work is equal to force times distance, right? Well, here we might have the piston having an area of A there, and we're pushing up here by some distance delta Y. Well, the pressure times that area, remember, pressure is force per unit area. The pressure times the area would be the force it's exerting. And then the delta Y would be how far it exerts that force. So here you could think of the work equaling the force exerted by the gas times delta Y, but the force is equal to the pressure times the area, and A times delta Y is the change in volume. So in this case, you'd have P delta V. Well, that's kind of what I drew here. The axis down here would be delta V, and this would be whatever the pressure happens to be. And so here, the work that would be done by the gas is just going to be the area, and I'm going to put that in air quotes because it's not actually an area, but it's the area that you can draw under that PV diagram. Well, it turns out that's always the way work is calculated, but sometimes the shapes aren't so nice. For instance, if you're coming down an isotherm like this, and here's your initial volume, and here's your final volume, and again, this is a PV diagram. Well, you'd have to calculate the area under here. Yeah, that's not going to be so easy, but what you do is you do the integral. The work is going to equal the pressure times dV as you're moving along whatever sort of curve you happen to have. And the way we figure out, you can't just, if it's not a constant pressure, there'll be some sort of a relation between the pressure and the volume that'll probably come out of the ideal gas law, like you might replace the pressure with nRT over V and integrate that, or something. There'll be some kind of condition that'll let you calculate that. So that's something that we'll be coming to here eventually. But for starters, let's do some problems that had some of those to do with those other things. The temperature near the top of Jupiter's multicolored cloud layer is 140 Kelvin, kind of chilly. The temperature at the top of the Earth's troposphere at an altitude of about 20 kilometers is about 220 Kelvin. Calculate the RMS speed of hydrogen molecules in both of these environments. Okay, well, this isn't too bad to do. It's we'll use we'll use VRMS. And remember, let's see, these are hydrogen molecules, so it'll just be 3K sub B times T divided by M. And for a hydrogen molecule, it's pretty much nothing but a proton. And so the mass of a proton, you can look it up, but it's 1.67 times 10 to the minus 27th kilograms. Or you could look at the molar mass of hydrogen, which is about 1 gram per mole, you can divide that by, or 1 times 10 to the minus third kilograms per mole, divide it by Avogadro's number, and you'd get just about that. In fact, I'm pretty sure we would. Um, divided by, oops. Yeah, well, I get 1.66 times 10 to the minus 27th, but close enough. Okay, so let's go to Jupiter first. And we'd have VRMS is going to be the square root of 3 times 1 point, wherever Boltzmann's constant went, was it 381 times 10 to the minus 23rd joules per Kelvin. Oh, then the temperature at Jupiter is 140 Kelvin. And for the second calculation, all I'm going to do is replace that 140 Kelvin with 220 Kelvin. And the mass down here, 1.67 times 10 to the minus 23rd kilograms. And we've done this before. The kelvins divide out because it's joules per Kelvin. I'll have joules over kilograms, and that's meters squared per second squared. So on Jupiter, let's see. Whoops, that's a minus 27 here, not 23. Okay, I get about 1.86 times 10 to the third meters per second. On Earth, at the top of the troposphere, is that what they said? Yes. Um, all I have to do is just change that 140 into 220. And it's not going to be a whole lot different. It's 1.62, 1.62 times 10 to the third meters per second. Okay, now it says give your answers in meters per second and as a fraction of the escape speed from the respective planet. Well, let's calculate those things. We know it for Earth, it's about 11.2 kilometers per second, if I remember right, but wouldn't hurt to recalculate that. So for Jupiter, the escape is going to be the square root of 2 times 6.67 times 10 to the minus 11th. That's the capital G. I don't know if you can read that formula or not, but um, Newton meters squared per kilogram squared. That's the gravitational constant. Times the mass of the planet, which for Jupiter, I need to look it up. I can't remember if it's 1.99 or 1.90. It's 1.90. Okay. Times 10 to the 27th kilograms. Oh, and I have to talk about R being the distance from the planet's center. I'm just going to use the radius of Jupiter, or the sort of radius of Jupiter. The top of its clouds, I guess. 6.91 times 10 to the 7th meters. And so escape speed from Jupiter Oh, let's see, another square root. Okay, and I get 6.06. I have three sig figs everywhere, times 10 to the fourth meters per second. So VRMS over V escape is going to be 1.86 times 10 to the third meters per second divided by the 6.06 times 10 to the fourth meters per second. And I get about 3.1 times 10 to the minus 2 is what I happen to get. So it's only the RMS speed is only about 3% of the escape speed. Okay. For Earth, it's a different picture though. Escape speed from Earth is 11.2. Actually, I should probably plug in the numbers, I guess. Actually, um, V escape, let's go ahead and use it. 11.2 times 10 to the third meters per second. So the VRMS over V escape for Earth is 1.62 times 10 to the third meters per second divided by 11.2 times 10 to the third meters per second, 11.2. So 1.62 divided by 11.2 is what it is. And I get about 0.14. So the RMS speed is actually about 14% of the escape speed. Now, the reason this matters, and part B has to do with this, hydrogen gas is a rare component in the Earth's atmosphere. In the, oh, let's see, actually for the hydrogen gas, um, I should have been using H2, I think. Yeah, I should have had a 2 down here, which would reduce all of these speeds by the square root of 2. But let's not worry about that for the moment. We'll just kind of look at these different values here, where this is only about 3% and this is about 14%. If you divided the RMS speeds by the square root of 2, I guess we get that, which means to multiply these by about 0.7. It'll have the same scale factor, but yeah, it'd be a little bit less than that. But anyway, it's a rare component in the Earth's atmosphere. Here's the thing about molecular speeds that it's discussed in one of the sections in chapter 18, but they're not all the same. And that's why we have to calculate a an average for them. And there's actually a section in chapter 18 on the distribution of molecular speeds and how they vary. But at a given temperature, it's a distribution that looks about like this. And the RMS value is actually out about here. Okay, it's a little ways past the peak because this isn't a symmetric curve. It's got a long tail going off to the right, and zero is down here. And this would represent the vertical axis is like the fraction of the particles with that speed. And so that's what it ends up looking like. And this curve is something you can figure out from statistical mechanics, and it was figured out experimentally in the 1800s by people who studied gases. And there's a little section about how you could measure those things. Anyway, um, there are particles out here that are a long ways past the RMS speed. In fact, they might be 10 times the RMS speed. Not a lot, but a few. But over time, especially over geologic time, what'll happen is those faster moving particles in that upper part of the atmosphere, some of them are going to be headed up, and there's not much air there anymore. If they've got a speed greater than the escape speed, they leave and don't come back. And after a little while, the gas speeds redistribute themselves, and you'll have some more particles going at that speed. And if they're up in the upper atmosphere and happen to be headed up, they'll leave and they won't come back. And over time, on the Earth at least, those things will gradually get out of there. But on Jupiter, wherever it went, where they've only got actually they'd have less than 3% of the escape speed, you'd be way farther out along this curve for the hydrogen gas on Jupiter, and you wouldn't be nearly as likely to lose the hydrogen gas on Jupiter because this thing gets smaller and smaller as you go out here. But it's an appreciable amount on Earth. So um, hydrogen gas is a rare component in the Earth's atmosphere, but in Jupiter, it's nearly the entire atmosphere, 90 or 89% of it. So there's that. Okay. Um, Suppose an astronomer claims to have discovered an oxygen atmosphere on Ceres. Ceres we dealt with, oh, on one of our problems in our gravitation unit. You imagine spinning it up to make it have an artificial gravity. But suppose somebody claims they saw oxygen in an atmosphere on Ceres, and it's got a mass of 1.0 times 10 to the 21st kilogram, radius of about 470 kilometers, mostly round, and a surface temperature of around 200 Kelvin. Well, let's figure out the escape speed from Ceres. V escape is going to be the square root of 2 times g times the mass of Ceres divided by its radius, and this would be the escape speed from the surface. So we'll just plug in the numbers and see what we get. And then we'll calculate the escape speed for an O2 molecule, or the RMS speed at 200 Kelvin. So we'd have 2 times 6.67 times 10 to the minus 11th Newton meter squared per kilogram squared. And I know I didn't go through the unit stuff for the planet Jupiter. We can talk about it here, I guess. Let's see. The mass of Jupiter is, or mass of Ceres, 1.0 times 10 to the 21st kilograms. Not much. GM. And then the radius, 470 kilometers, which is 470 times 10 to the third meters. Let's see how this will work out. A Newton is a kilogram meter per second squared. So there'd be a kilogram and a kilogram and kilograms squared there. So the kilograms are gone. Meter per second squared is left, so I'd have meters cubed per second squared, but I'm dividing by meters, so I'd have meters squared per second squared, and I take a square root. So yes, the units work out. And I know I did that fast, but so let's figure out the escape speed from Ceres. 2 times And I get an escape speed that isn't much. Um, we keep two significant figures. Basically, 530 meters per second is all the bigger the escape speed is from series. Now, the VRMS, or an oxygen molecule, remember it's the square root of 3k sub b T divided by the mass of the particle. And for an oxygen molecule, it'll be approximately 32 times the mass of a proton. So 3 times the 1.381 times 10 to the minus 23rd joules per Kelvin. Eventually, I might just have Boltzmann's constant memorized. It hangs on for a little while and then I forget it. And let's see, what temperature did we have? 200 Kelvin. And then divide by 16 times the mass of a proton or neutron, 1.67 times 10 to the minus 27th kilograms. So we can figure out the RMS speed. And my guess is even at 200 Kelvin, it might be a few hundred meters per second. So hmm, I don't know if I put these numbers in right. 3K T. Hmm. I don't know. I got an RMS speed of 570 meters per second, which I think is higher than I had when I did it at room temperature for an oxygen molecule. I may have, no, that just doesn't look right. Um, oh, I know what went wrong. I put a 16 down here and it should have been 32. There we go. Okay. Yeah, because there's 16 protons and 16 neutrons. Okay, that's better. I get about 394 meters per second. Okay, well, here's what happens with that distribution of molecular speeds. We've got the RMS speed here. We'd only be out about, well, not much farther, not much farther there to get to the 530 meters per second. So a fairly significant chunk of the particles are going to have speeds greater than the escape speed from series. And over time, those would leave and not come back. And then the particles redistribute their speeds, and there's like a constant evening out of the molecular speeds. And this curve would just get flatter and flatter and flatter. And eventually, all of those O2 molecules would leave. So someone claiming to see an oxygen atmosphere on series better check their data and do a little bit of reinterpretation of that because it doesn't appear to be correct. Okay, that's just been some stuff dealing with the molecular speeds, but let's do one with the heat capacity of a gas. And the door to a mostly empty refrigerator is open for about 2 minutes while a human browses its contents. Well, if it's mostly empty, I don't know what they're going to be looking at, but that's okay. Anyway, when the door is shut, when they finally shut it, all of the air in the refrigerator has been exchanged with room temperature air if the volume of the refrigerator is 28 cubic feet. From this, calculate the heat capacity of the air in a refrigerator and compare this to the heat capacity of 1 liter of water. Well, the first thing I'm going to have to do is convert 28 cubic feet. And the reason the original problem said something like estimate the volume of the refrigerator and figure if you're not someone who's ever bought a refrigerator, you'd never know this. But this is a volume of a refrigerator that you might buy. So anyway, we have to fix that. So 28.0 feet cubed times the number of feet in a meter or something like that. Conversion factors, length. 1 foot is 0.305 meters. So 0.305 meters per foot, and we have to cube that. So and I get 0.79. And I'm not going to try to get very many significant figures on this thing. It's kind of ridiculous. And also, if there's junk in the refrigerator, that would actually reduce the capacity that's available for air. So good enough. That much in the way of meters cubed. Now, how are we going to figure out the density of air or the mass of the air in there? Well, that's the volume. The density of air is about, I don't know if we've got that in the front of the book or not. Um, I can't remember if it's 1.20 or 1.29, but I'll just use the lower value because I think it'd be cold air. Yeah. Um, that's the density of the air approximately. So the mass of the air, the volume is this. The mass is going to be the density times the volume. And so 0.79 times, well, yeah, just or meters cubed times that 1.20 kilograms per cubic meter. So then there'd be about 0.95 kilograms of air in the refrigerator. Okay, and then what did we have? Oh, we had a molar heat capacity is what we have for a diatomic gas. The C sub V, the constant volume heat capacity, is 5 halves R. And the amount of heat needed to increase the temperature of something, Q, would end up equaling, in this case, it'd be the number of moles times the molar heat capacity times the temperature difference. Okay, well, that's kind of complicated. Now we have to do some chemistry. We have 0.95 kilograms of air. How many moles of air is that? All right, somebody who's taken chemistry this quarter, who's doing it? Um, I don't know if Alyssa's on here or not. Maybe she is. This will put her on the spot. Nope, she's not. Okay. Oh man, it's a mixture of nitrogen and oxygen. Yuck, what a mess. Uh, I may have to look that up. I don't know. Um, there's a little section on this stuff in molecular properties of matter. Um, oh well, I know how to do it. Oh yes, they do have it for oxygen at least. Um, let's see. The molar mass of air, it's, oh man. Oh well, let's just estimate it. And it's about 32 grams per mole. That's the molar mass for oxygen and equals 0.032 kilograms per mole. So if I take this point 0 or 0.95 kilograms and multiply it by 1 mole over 0.032 kilograms, I'll get the number of moles of if we just had pure oxygen in there. And um, it's a mixture of oxygen and nitrogen, so I'd have to use something a little bit different than this, but 0.95 divided by 0.032, and I get about 30. Yeah, 30 moles. Okay. So actually, we were just supposed to figure out the total heat capacity, which is this. We don't have to worry about a delta T here. All of the air in the refrigerator has been exchanged if the volume of the refrigerator is that. Calculate the heat capacity of the air in a refrigerator. Okay, so I just have to take this 30 moles and multiply by NC sub B. So um, 30 times, and this is two significant figures, so I can put a dot there, but I don't like that. Um, times 5 halves times 8.314 joules per Kelvin mole, I guess is what we're doing here. So, oh, and this is moles. So this will be a result in joules per Kelvin, and I get about 620, well, let's just say 620 for comparison, joules per Kelvin. All right. Well, what about the heat capacity of 1 liter of water? In that case, the heat capacity would be the mass times the specific heat of water times L, which is back a ways in the previous chapter. Quantity of heat, specific heat of water. A liter of water has a mass of 1 kilogram, and gotta have water. Here we go. 4,190, whoops, times joules per kilogram Kelvin. So I'd basically end up with 4,190 joules per Kelvin. Whoops, 90, which is basically about 7 times as much as the heat capacity of the air in the refrigerator just for 1 liter of water. So if you had, like, say, a gallon of milk in there, that's about 3.8 liters. So you'd have a number 3.8 times as high as that. And if you had a couple 6 packs of pop or something like that in there, you'd be way out. So losing this little bit of replacing that air with room temperature air is not going to have much effect. Anyway, okay, I didn't get to a lot of other problems today, so we'll save some of those for tomorrow and move on from there. By the way, I changed some of my computer settings at home. I don't know if it should have made any difference. Does this look any clearer than it has in the past? Or is it still about the same amount of fuzziness? And you could just type something in there or unmute your microphone if you want. But just curious. Oh, I can stop recording.